What does it actually mean to say that the universe is large? The word appears constantly in discussions about space, yet it hides a scale so extreme that ordinary language begins to fail. Large compared to a planet, large compared to a galaxy, large compared to every structure humanity has ever imagined. But even these comparisons barely scratch the surface, because the universe is not simply large in the way an ocean or a mountain range is large. It is large in a way that bends the limits of perception itself. Every night the sky offers a quiet illusion, a scattering of distant lights arranged across a black canvas, points that seem close together, as though they exist on a flat dome above the Earth. For most of human history, that illusion felt natural. Stars appeared as distant but fixed objects embedded in a cosmic ceiling. The universe seemed vast but still contained. Modern astronomy revealed something far stranger. Those points of light are not attached to a surface. They are not arranged on a nearby shell. They are scattered across distances so enormous that the concept of distance itself begins to lose meaning. Some of those lights belong to stars within our own galaxy. Others belong to galaxies millions or billions of light years away. And each of those galaxies contains hundreds of billions of stars of its own. Yet even this description hides the most unsettling detail of all. The night sky is not showing the universe as it exists now. It is showing fragments of the past. Light moves quickly. In everyday life, it appears instantaneous. But the universe operates on scales where even the speed of light becomes slow. The moment light leaves an object, a journey begins. A photon travels outward across space until it encounters something capable of detecting it. A telescope mirror, a camera sensor, a human eye. During that journey, time continues to pass. When light from the sun reaches Earth, it has already been traveling for roughly 8 minutes. The sun seen in the sky belongs to the past. If the sun were to suddenly vanish, its disappearance would not be visible immediately. The light already on its way would continue arriving for those same 8 minutes. The moon appears closer, yet its light also carries a delay. The lunar surface visible in the night sky shows the moon as it existed roughly 1 second earlier. That delay is small, almost meaningless on human timescales, but it reveals something profound about the universe. Distance and time are inseparable. As observation pushes farther outward, the delay grows larger. The nearest star beyond the sun appears as it was more than 4 years ago. The center of the Milky Way arrives 26,000 years late. The Andromeda Galaxy appears as it existed roughly 2.5 million years in the past. Every step outward becomes a deeper step backward in time. The sky is not a live display of the universe. It is a layered archive. Every photon carries a timestamp from the moment it began its journey. Some of the light reaching Earth tonight left its source long before human civilization existed. Some left before Earth itself had formed. For astronomers, this strange property transforms telescopes into time machines. Looking across the universe means looking into earlier and earlier chapters of cosmic history. Nearby objects reveal the present era of the cosmos. Distant galaxies reveal a younger universe. The most distant light shows conditions close to the beginning of everything. But there is a complication hidden inside this cosmic time machine. The universe is not static. Space itself is expanding. For a long time, the expansion of the universe was misunderstood as galaxies flying outward through empty space, similar to fragments thrown outward by an explosion. The image is vivid, but it is wrong. Galaxies are not racing through space away from a central point. Instead, the fabric of space itself is stretching. A simple picture helps reveal the difference. Imagine a balloon covered with small dots. As the balloon inflates, the distance between every pair of dots increases. None of the dots are moving across the surface. The surface itself is expanding, carrying the dots apart. The universe behaves in a similar way. Galaxies remain mostly stationary within their local regions, while the space between them slowly stretches. This expansion changes the journey of light. When a photon travels across expanding space, its wavelength stretches along with the universe. Short, energetic wavelengths slowly lengthen during their journey. Blue light shifts toward red. Red light stretches further into infrared. Astronomers call this effect redshift. Redshift is not simply a change in color. It records how much the universe has expanded while the light was traveling. The more stretched the light appears, the longer its journey has been, and the earlier in cosmic history it was emitted. For decades, this effect created a frustrating barrier for astronomers. The earliest galaxies formed when the universe was young. Their light began its journey billions of years ago. During that immense travel time, the expansion of space stretched much of their radiation out of the visible range entirely. By the time that ancient light reached Earth, it no longer appeared as visible starlight. It had shifted into infrared wavelengths invisible to the human eye. Earlier telescopes were not designed to see it. Instruments such as the Hubble Space Telescope revolutionized astronomy by capturing extraordinary images of galaxies and nebulae in visible light. But as observations pushed deeper into the universe, something puzzling happened. The cosmos began to fade. Regions of the early universe appeared strangely dark. Galaxies that should have existed were difficult to detect. Large portions of cosmic history seemed hidden. The darkness was not empty space. It was unreadable light. Astronomers realized that the earliest galaxies had not disappeared. Their light had simply drifted beyond the range of the instruments used to observe them. To see the distant past required a new kind of telescope, one built specifically to detect infrared radiation. That telescope became the James Webb Space Telescope. Webb was designed with a mirror more than 6 meters across, made from 18 precisely aligned hexagonal segments coated in a thin layer of gold. Gold reflects infrared light extremely efficiently, allowing the mirror to gather ancient photons stretched by billions of years of expansion. The telescope does not orbit Earth like Hubble. Instead, it operates far beyond the Moon at a location known as the second Lagrange point, roughly 1 million miles from Earth. At that distance, the Sun, Earth, and Moon remain in the same general direction, allowing a massive multi-layer sunshield to permanently block their heat and light. This design is critical. Infrared radiation is closely associated with heat. Any warm object glows faintly in infrared wavelengths. A warm telescope would drown out the faint signals it is trying to observe. Webb therefore operates at extremely low temperatures. On the shadowed side of its sunshield, the telescope cools to temperatures where even incredibly faint infrared photons can be detected. Only under those conditions can light that has traveled for billions of years finally be recorded. When Webb turns toward a region of sky that appears completely black to human eyes, it is not searching for emptiness. It is collecting ancient photons arriving slowly from distant galaxies. These photons do not arrive in great bursts. They appear gradually, sometimes one at a time, after journeys spanning most of cosmic history. Webb may stare at the same patch of sky for many hours or even days, patiently gathering enough light to construct a meaningful image. When those observations are combined, something remarkable appears. Galaxies begin to emerge. Structures that once seemed absent reveal themselves as faint infrared glows. Systems already forming stars. Clusters of matter gathering under gravity. Entire populations of galaxies hidden beyond the reach of previous telescopes. The early universe does not appear empty. It appears busy, This realization carries an unsettling implication. Many of the galaxies Webb detects formed far earlier than astronomers expected. According to traditional models, galaxy formation was supposed to be slow. After the Big Bang, the universe expanded and cooled. Matter spread out across space with only tiny irregularities in density. Gravity gradually amplified those irregularities, slowly pulling gas together to form the first stars. This process was expected to take time. Stars require dense gas clouds to collapse under gravity. Those clouds must cool and compress before nuclear fusion ignites. Galaxies grow through repeated mergers and steady accumulation of matter. Each step introduces delays that limit how quickly structure can emerge. Yet Webb began detecting galaxies that appeared surprisingly mature when the universe was still extremely young. Some existed within the universe's first few 100 million years. Others already contained enormous numbers of stars, implying that intense star formation had been underway long before their light began traveling toward Earth. The early universe appeared brighter than expected. Astronomers began referring to the phenomenon informally as the too much too early problem. Simply put, galaxies seemed to be assembling faster than many models predicted. This discovery does not mean that cosmology is wrong. Instead, it highlights how incomplete our understanding of the early universe remains. Several explanations may contribute. Conditions in the early cosmos were far denser than today. Matter occupied a much smaller volume of space, allowing gas clouds to collide and compress more frequently. Rapid mergers between young galaxies could trigger powerful bursts of star formation. The first generations of stars may also have been far more massive than those forming today, producing intense radiation and heavy elements very quickly. Another mystery appears at the centers of some early galaxies: supermassive black holes. Webb has detected evidence that some galaxies less than 500 million years after the Big Bang already hosted black holes containing millions or even billions of solar masses. Growing a black hole to that size usually requires immense time. Stellar collapse typically produces black holes only a few times the mass of the Sun. From there, they must accumulate matter gradually. Yet these early black holes appear far larger than expected for such a young universe. One possible explanation involves the direct collapse of enormous gas clouds, producing massive black hole seeds from the beginning. Another possibility is that early stars were extremely massive and short-lived, collapsing quickly into larger black holes that then grew rapidly in dense environments. At present, the details remain uncertain. What is clear is that the early universe was far more active than once imagined. Galaxies were assembling, stars were igniting, and black holes were growing during a period once thought to be mostly dark and uneventful. These galaxies did not form randomly throughout space. Their distribution follows a pattern that emerges only when enormous regions of the universe are mapped together. On the largest scales, the universe resembles a vast interconnected network known as the cosmic web. Filaments of matter stretch across distances of tens and hundreds of millions of light-years. These filaments intersect at dense nodes where clusters of galaxies gather under gravity. Between the filaments lie enormous voids, regions where very little matter accumulated. The cosmic web represents the large-scale architecture of the universe. After the Big Bang, matter was distributed almost uniformly across space, with tiny variations in density. Over time, gravity amplified those variations. Regions slightly denser than their surroundings attracted more matter, growing into filaments and clusters while surrounding regions were gradually emptied. The result resembles a complex network of strands threading the cosmos. Galaxies form along these strands where matter collects most efficiently. Gas flows along the filaments, feeding star formation and allowing galaxies to grow. The cosmic web therefore acts as the scaffolding on which the visible universe is built. Webb's deep surveys have helped reveal this structure with increasing clarity. By detecting enormous numbers of distant galaxies and measuring their distances, astronomers can map how matter is arranged across space and time. Patterns that once appeared incomplete now reveal extended filaments and clusters stretching across vast cosmic distances. Yet even this enormous network represents only a small fraction of the universe. Because every observation made from Earth is limited by a boundary imposed by physics itself. The observable universe. The observable universe is not the entire universe. It is the portion of reality whose light has had enough time to reach us since the beginning of cosmic expansion. Every telescope, every detector, every observation ever made operates within this invisible boundary. The boundary does not represent the edge of space. It represents the edge of information. Beyond it, the universe continues. To understand why this limit exists, it helps to return once again to the relationship between distance and time. The universe began approximately 13.8 billion years ago, in a state of extraordinary density and temperature. In the earliest moments, matter and radiation were compressed into a hot plasma where light could not travel freely. Only after the universe expanded and cooled enough for electrons and atomic nuclei to combine did photons begin moving across space without constant scattering. That moment released a faint glow that still fills the universe today. This radiation is known as the cosmic microwave background. It represents the oldest light that can ever be observed directly. When telescopes detect it, they are seeing the universe as it existed only a few 100,000 years after the Big Bang. But even after light began traveling freely, its journey remained limited by time. A photon emitted at that early moment has been traveling for billions of years. During that time, the universe itself has continued expanding. The distance between galaxies has steadily grown while the photon moves through space. As a result, the universe we observe today is far larger than intuition suggests. At first glance, it might seem natural to assume that the most distant observable objects should lie roughly 13.8 billion light-years away. After all, if light has been traveling for 13.8 billion years, that distance appears to be the maximum possible. Yet observations reveal a much larger value. The observable universe has a radius of roughly 46 billion light-years. From one side to the other, it spans approximately 93 billion light-years. This does not violate the cosmic speed limit. No object has traveled through space faster than light. Instead, space itself has stretched while light was moving through it. The galaxies that emitted the most ancient light we detect today were much closer to us when that light began its journey. Over billions of years, the expansion of space carried those galaxies far farther away. In effect, the photons were traveling across a moving landscape. While they moved forward, the ground beneath them was stretching. This expansion creates the horizon that defines our observable universe. There are regions of space so distant that the light emitted there has simply not had enough time to reach Earth. Their photons are still traveling across expanding space, slowly approaching but not yet arriving. Given enough time, some of that light will eventually reach us, gradually enlarging the observable universe. But another effect complicates this picture. The expansion of the universe is not constant. It is accelerating. During the 20th century, astronomers expected gravity to slow cosmic expansion over time. Matter pulls matter inward, and on the largest scales, the combined gravity of galaxies and clusters should gradually reduce the rate at which space expands. Observations eventually revealed the opposite. Measurements of distant stellar explosions known as Type 1 supernova showed that galaxies are receding faster today than they were billions of years ago. Instead of slowing down, cosmic expansion has been speeding up. Something is pushing space apart. This mysterious influence is known as dark energy. Dark energy does not interact with light in any detectable way. It produces no radiation and forms no structures. Yet its effects dominate the large-scale behavior of the universe. Measurements suggest that dark energy makes up roughly 2/3 of all energy in the cosmos. Ordinary matter, including stars, planets, gas, and dust, represents only a small fraction. Even dark matter, the invisible mass responsible for holding galaxies together, accounts for less than 1/3 of the total cosmic energy budget. Dark energy appears to behave very differently from ordinary matter. As the universe expands, the density of normal matter decreases because it spreads across a larger volume of space. Double the size of space and the density of matter becomes half as great. Dark energy does not dilute in the same way. Its density appears to remain constant even as the universe expands. As more space forms, the total amount of dark energy increases. This creates a subtle but powerful feedback effect. More space leads to more dark energy. More dark energy drives faster expansion. Faster expansion creates still more space. Over billions of years, this effect has gradually taken control of the large-scale universe. In the early cosmic era, gravity dominated. Matter gathered into clouds, stars ignited, and galaxies assembled along the filaments of the cosmic web. But as expansion continued, matter became increasingly diluted. Dark energy eventually overtook gravity as the dominant influence on cosmic expansion. From that moment onward, the universe began accelerating outward. This acceleration has consequences for what can be observed. Galaxies that are extremely distant today may eventually drift beyond the observable horizon. Their light will become increasingly stretched and diluted until it can no longer reach Earth at all. In the far future, observers within the Milky Way may see only a handful of nearby galaxies. The rest of the cosmos will fade beyond the horizon created by accelerating expansion. Yet even this immense observable region represents only a small portion of reality. Because the universe does not suddenly stop at the cosmic horizon. Everything astronomers have measured suggests that space continues far beyond what can be observed. The distribution of galaxies does not thin toward an edge. The cosmic microwave background appears nearly uniform across the entire sky. These observations strongly imply that the universe extends far beyond the limits of our vision, perhaps infinitely far. In that unseen expanse, galaxies continue forming, stars ignite and die, and entire cosmic histories unfold forever beyond our reach. No signal from those regions will ever arrive at Earth. Not because technology is insufficient, but because the expansion of space itself prevents it. Every observer in the universe therefore exists inside a personal bubble of visibility. Move to another galaxy and the observable universe would look different. Some regions visible from Earth would disappear beyond the horizon, while new regions would come into view. No location offers a complete perspective. There is no center from which the entire universe can be seen. Each vantage point reveals only a fragment. And yet, even within that fragment, the scale of reality remains staggering. Modern observations suggest that the observable universe may contain trillions of galaxies. Each galaxy holds millions, billions, or even trillions of stars. Around many of those stars orbit planetary systems that may contain worlds of every imaginable kind. The universe is not sparsely populated. It is crowded beyond imagination. But the luminous matter visible in stars and galaxies represents only a small portion of the total cosmic structure. Most of the mass shaping the universe remains invisible. That hidden component is known as dark matter. Dark matter reveals itself not through light, but through gravity. When astronomers observe the motion of stars within galaxies, something unexpected appears. Stars near the outer edges of galaxies move far faster than visible matter alone can explain. According to the laws of gravity, those stars should escape into intergalactic space, yet they remain bound in stable orbits. The only consistent explanation is that galaxies are embedded within enormous halos of invisible mass, extending far beyond their visible edges. This unseen mass outweighs ordinary matter by several times and creates the gravitational wells that hold galaxies together. Without it, the structures that fill the night sky would never have formed. Evidence for dark matter appears across many different scales of observation. Entire galaxy clusters exhibit gravitational effects that cannot be produced by visible matter alone. When light from distant galaxies passes near these clusters, it bends, producing distorted arcs and rings known as gravitational lenses. Careful measurements revealed that the amount of mass required to produce these distortions is far greater than the mass contained in stars and gas. Something invisible must be contributing the missing gravity. Unlike ordinary matter, dark matter does not collide with itself or emit radiation. It passes through space almost without friction. Because of this unusual behavior, it began clumping extremely early in cosmic history, long before gas clouds were able to cool and collapse. Tiny density variations present after the Big Bang gradually grew as dark matter gathered into increasingly large halos. These halos acted as gravitational anchors that later drew ordinary matter inward. Gas flowed into these wells, compressed under gravity, and eventually ignited the nuclear reactions that produce stars. In this way, dark matter formed the invisible foundation upon which the visible universe was built. When cosmologists simulate the evolution of the universe inside powerful computers, they see a remarkable pattern emerge. Dark matter gathers along elongated strands, gradually forming an immense network that stretches across cosmic space. At the intersections of these strands, enormous clusters of galaxies appear, while vast empty regions form between them where little matter collects. The resulting structure resembles a web, delicate yet immense, spanning hundreds of millions of light years. The cosmic web is not merely a theoretical concept. Observations increasingly reveal its presence. Surveys of distant galaxies show that they are not scattered randomly across space. Instead, they trace long filaments that extend across immense distances. Gas flows along these filaments toward dense nodes, where galaxy clusters grow larger over time. These clusters act as gravitational anchors within the web, pulling matter inward while surrounding voids continue expanding. The existence of this structure helps explain one of the most striking characteristics of the universe. On the largest scales, matter appears organized rather than chaotic. Galaxies follow patterns shaped by gravity over billions of years, gradually assembling into networks that connect across enormous distances. Yet between those filaments lie some of the largest structures known in nature. Cosmic voids stretch across tens of millions of light years, containing very few galaxies at all. If an observer could stand at the center of one of these voids, the surrounding universe would appear almost completely dark. This interplay between dense filaments and empty voids illustrates a fundamental feature of cosmic evolution. Gravity gathers matter where it already exists, while leaving surrounding regions increasingly empty. Over time, this process exaggerates the contrasts in the universe, producing a landscape where clusters grow richer and voids grow emptier. Even this vast structure, however, did not arise from perfectly smooth beginnings. The seeds of the cosmic web were planted far earlier, during a brief and mysterious moment known as cosmic inflation. Inflation refers to a period in the earliest fraction of a second after the Big Bang, when the universe expanded extraordinarily rapidly. During this moment, space itself stretched at a pace far exceeding the expansion that followed. Regions that were once extremely close together were suddenly separated by enormous distances. Tiny fluctuations present in the primordial universe were magnified during this expansion, imprinting subtle variations in density across space. These variations later became the starting points for structure formation. Regions that were slightly denser than average attracted more matter through gravity. Over billions of years, those regions evolved into galaxies, clusters, and the filaments of the cosmic web. Inflation therefore shaped the large-scale architecture of the universe long before the first stars existed. Evidence for inflation appears in the remarkable uniformity of the cosmic microwave background. This ancient radiation fills the entire sky with nearly identical temperature in every direction, yet careful measurements revealed tiny variations only a few parts in 100,000. These minute fluctuations correspond precisely to the density differences required to form the cosmic structures observed today. Without inflation, the universe would appear very different. Large regions of space would likely have evolved independently, producing a cosmos far less uniform than the one observed. Inflation provides a mechanism for explaining why the observable universe shares similar properties across enormous distances. Yet inflation raises profound questions of its own. If space expanded so rapidly during the earliest moments, it may have stretched far beyond the limits of what can ever be observed. Some models suggest that inflation did not occur just once, but may continue occurring in distant regions of space, creating new, expanding domains of universe in an ongoing process. This possibility leads to one of the most radical ideas in modern cosmology. The observable universe may represent only a tiny portion of a far larger cosmic landscape. Beyond the limits of observation space could continue indefinitely, perhaps containing countless regions similar to our own. Other theories suggest that the universe might be finite but curved, wrapping around itself in ways that would eventually bring a traveler back to the starting point after an unimaginably long journey. Determining the true shape and extent of the universe remains one of the most difficult problems in cosmology. For now, the observable universe provides the only region that can be studied directly. Within its 93 billion light-year span, astronomers continue uncovering new structures, new galaxies, and new clues about cosmic history. Telescopes such as James Webb extend the reach of observation deeper into time, allowing glimpses of the universe during its earliest stages of development. Yet even Webb cannot cross the fundamental boundary imposed by cosmic expansion. There will always remain regions of the universe whose light will never reach Earth. Their histories unfold beyond every telescope and detector that can ever be built. Understanding this limitation changes the meaning of observation itself. When astronomers map the universe, they are not mapping the whole of existence. They are mapping the portion that happens to be visible from one location during one brief moment of cosmic time. Move billions of light-years away, and the observable universe would shift. New regions would come into view, while others disappear beyond the horizon. Every galaxy therefore sits at the center of its own observable bubble, surrounded by a slightly different slice of cosmic history. This realization carries a strange implication. Two distant galaxies might both be visible from Earth, while remaining permanently invisible to one another. Light from each galaxy can reach us, yet the distance between them may be too large for their light to ever cross. The universe allows many perspectives, but none that reveal everything. Despite these limits, the progress of cosmology over the past century has transformed humanity's understanding of the cosmos. Observations have expanded the known universe from a single galaxy to a vast network of trillions. The discovery of dark matter revealed the invisible scaffolding holding galaxies together. the discovery of dark energy showed that cosmic expansion is accelerating. Each discovery has enlarged the scale of the universe beyond what earlier generations imagined possible. And yet the deeper scientists look, the more the universe reveals how much remains unknown. Dark matter has never been directly detected, despite decades of experiments designed to observe it. Dark energy remains almost entirely mysterious, known only through its effects on cosmic expansion. Even the earliest moments of the Big Bang remain hidden behind conditions that current physics cannot fully describe. What emerges from these discoveries is not a complete picture, but an expanding frontier of knowledge. The universe grows larger, not only in physical scale, but in intellectual depth, as each new observation reveals further questions. Perhaps the most humbling realization of all is that the portion of reality humanity can observe represents only a fraction of what exists. Beyond the observable horizon, the universe continues unfolding in ways that may never be directly witnessed. Entire galaxies may rise and fall, stars may ignite and vanish, and structures may form across distances forever hidden from view. The night sky, therefore, represents both a revelation and a limit. Every point of light carries information from a different moment in cosmic history, allowing glimpses of events that occurred billions of years ago. Yet each observation also reminds us that most of the universe remains beyond reach, separated not by technology, but by the fundamental behavior of space and time. In that sense, the universe revealed by modern astronomy is both immense and incomplete. It is a vast landscape filled with galaxies, dark matter, expanding space, and hidden regions that stretch far beyond observation. And as telescopes continue probing deeper into the cosmos, they reveal not the edge of reality, but the depth of the mystery that still surrounds it. One of the most intriguing problems in modern cosmology concerns something that might appear deceptively simple. How fast is the universe expanding today? At first glance, this might seem like a question with a straightforward answer. Yet measurements performed using different methods continue to produce slightly different results. When astronomers look far into the past by studying the faint glow of the cosmic microwave background, they infer an expansion rate that is slightly slower than the value obtained when measuring distances to nearby galaxies using supernova and pulsating stars. Both techniques are extraordinarily precise, and both are being refined repeatedly over the past decades. Yet the discrepancy remains. This puzzle has become known as the Hubble tension, and it hints that some aspect of cosmic evolution may not yet be fully understood. The difference is small, but in cosmology, even a small difference can carry enormous implications. If the expansion rate has changed in unexpected ways over time, it could alter estimates of the universe's age, its total size, and the behavior of dark energy itself. Resolving this tension has become one of the most important goals of modern observational astronomy. The James Webb Space Telescope contributes to this effort by improving measurements of distant stars and galaxies, allowing astronomers to refine the cosmic distance ladder used to calculate expansion rates. Early results suggest that the higher expansion value measured in the nearby universe may indeed be correct, which would imply that something unusual occurred in the early universe to change the rate at which space expanded. Some theories propose that dark energy may evolve slowly over time, rather than remaining perfectly constant. Others suggest the presence of additional particles or forms of energy that briefly influenced the early cosmos before fading away. At present, the evidence remains inconclusive, but the possibility that the universe may behave differently than current models predict continues to drive new observations and new theoretical work. While cosmologists debate the exact behavior of cosmic expansion, another question emerges naturally from the discovery of accelerating space. What will the universe look like in the distant future? The answer depends on how dark energy continues to behave. But if the current acceleration persists, the long-term fate of the cosmos will become increasingly quiet and isolated. Over tens of billions of years, the expansion of space will gradually carry most galaxies beyond the observable horizon. The gravitational pull within galaxy groups will keep nearby systems bound together, but everything beyond those local clusters will drift farther and farther away. Eventually, observers living inside a galaxy like the Milky Way would see only a small collection of neighboring galaxies surrounded by an enormous darkness. In that far future, the universe would appear far smaller than it does today, even though its true size would be vastly larger. The evidence of cosmic expansion, the faint glow of the cosmic microwave background, and the distant galaxies that today fill deep space images would all fade from view. Future astronomers might conclude that their galaxy cluster represents the entire universe, simply because every other structure would have slipped beyond the horizon of observation. The universe would still contain trillions of galaxies spread across unimaginable distances, but their light would never reach those future observers. This gradual isolation marks the beginning of a much longer transformation that unfolds across trillions of years. During the present era, the universe is rich with stars, galaxies, and active processes that release enormous amounts of energy. This period is sometimes called the stellar era, a time when nuclear fusion inside stars provides the primary source of light and structure. Stars form from collapsing clouds of gas, shine for millions or billions of years, and eventually exhaust their fuel, leaving behind stellar remnants such as white dwarfs, neutron stars, and black holes. As time progresses, star formation will slowly decline. The gas required to create new stars will become increasingly scarce as it is consumed by previous generations. Galaxies will gradually lose their ability to produce new stellar systems. Over hundreds of billions of years, the brilliant star-filled universe visible today will fade as the last generations of stars burn through their remaining fuel. What follows is sometimes called the degenerate era. During this stage, the universe becomes dominated by stellar remnants. White dwarfs cool slowly into dark, crystalline objects. Neutron stars remain as incredibly dense spheres composed almost entirely of neutrons. Black holes persist as the most extreme objects known in nature, containing gravity so strong that not even light can escape. Even these remnants will not last forever. Over extremely long timescales, gravitational interactions gradually reshape galaxies, sending stars drifting away or falling inward towards central black holes. Occasional collisions between stellar remnants release brief bursts of energy, but the overall trend continues toward darkness and stillness. The universe becomes a far quieter place compared to the vibrant era of star formation that exists today. Black holes eventually dominate the final chapters of cosmic evolution. These objects, once thought to be perfectly eternal, are predicted to slowly lose mass through a subtle quantum process known as Hawking radiation. Over timescales vastly longer than the current age of the universe, black holes gradually evaporate, releasing faint radiation as they shrink. Massive black holes at the centers of galaxies could persist for unimaginable spans of time before finally dissolving into streams of low-energy particles. When the last black holes eventually disappear, the universe may enter its final stage, sometimes referred to as the dark era. At this point, almost no organized structure remains. The cosmos becomes filled primarily with extremely dilute particles and faint radiation spread across an immense volume of space. Energy differences between regions approach equilibrium, leaving very little activity or change. The universe reaches a condition often described as heat death, where the ability to perform useful work has effectively vanished. Although this distant future unfolds across timescales so enormous that they are difficult to imagine, it follows naturally from the physical laws that govern matter gravity, and thermodynamics. The universe evolves from a hot, dense beginning toward an increasingly cold and diffuse state. Structures form, shine, and eventually dissolve as energy spreads more evenly across space. Yet even in this quiet future, the universe will remain unimaginably large. Space will continue expanding, carrying the remaining particles farther apart, while dark energy drives the cosmic acceleration that began billions of years earlier. The vast emptiness that emerges will represent the final stage of a universe that once contained brilliant galaxies, luminous stars, and complex structures stretching across the cosmic web. Reflecting on this immense timeline reveals how brief the present moment truly is. Humanity exists during a remarkably active period of cosmic history, a time when stars still shine brightly and galaxies remain visible across enormous distances. The universe today is filled with light and structure, allowing astronomers to observe and study processes that will eventually disappear. Modern telescopes therefore capture a temporary chapter in cosmic history. Instruments such as the James Webb Space Telescope allow astronomers to glimpse galaxies forming during the earliest epochs of the universe, while also observing the mature structures that populate the cosmos. Today, these observations connect the beginning of cosmic structure to the present era, revealing a narrative that spans billions of years. The story that emerges is one of transformation on a scale far beyond everyday experience. From tiny fluctuations in the earliest universe arose the vast network of galaxies and filaments that fill space today. Invisible components such as dark matter shaped the gravitational framework of that structure, while dark energy continues driving the expansion that stretches the universe ever larger. Each discovery deepens our understanding of the cosmos, while also revealing how much remains unknown. The nature of dark matter remains one of the most persistent mysteries in physics. The origin of dark energy remains almost entirely unexplained. Even the precise conditions that existed during the first moments after the Big Bang continue to challenge the limits of current theories. Yet despite these unanswered questions, the broad outline of cosmic history has become increasingly clear. The universe began in a hot, dense state, expanded and cooled, formed stars and galaxies, and continues evolving today as expansion accelerates. Within this immense process, humanity occupies only a tiny moment, observing the cosmos from a single location inside one galaxy among trillions. Seen from that perspective, the night sky takes on a new meaning. Each faint point of light represents a galaxy filled with countless stars. Each photon arriving at a telescope carries information from a distant moment in time. Together, these signals allow astronomers to reconstruct the history of a universe far larger and older than any earlier civilization could have imagined. And yet even this extraordinary view remains incomplete. The observable universe represents only the region whose light has had time to reach us since the beginning of cosmic expansion. Beyond that horizon, the universe almost certainly continues, filled with galaxies and structures that will remain forever beyond observation. In that sense, the most profound discovery of modern cosmology may not be the size of the universe itself, but the realization that what we can observe is only a fragment of a much larger reality. The cosmos revealed by our telescopes is vast beyond comprehension, yet it may represent only a small window into an even greater expanse that stretches far beyond the limits of human sight. The deeper we look into space, the more the universe reveals both its grandeur and its mystery. Every observation expands the known boundaries of cosmic history, while reminding us that the majority of existence remains hidden beyond the horizon. In that endless balance between knowledge and mystery lies the quiet wonder that continues to drive the exploration of the universe. When astronomers look outward across billions of light years, They are not only observing distant galaxies, they are also observing the limits of knowledge itself. Every telescope ever built operates within the same fundamental constraint imposed by the finite speed of light and the expansion of space. The deeper instruments peer into the cosmos, the closer they approach a boundary where information itself becomes unreachable. The observable universe therefore represents a rare window in cosmic history, a period when enough light from distant regions has arrived to reveal a vast network of galaxies while still leaving much of the universe hidden beyond the horizon. This perspective reshapes the way the universe is understood. Earlier generations imagined the cosmos as something that could eventually be mapped completely, as though the entire structure of reality might one day lie within the reach of observation. Modern cosmology suggests a very different picture. Even with unlimited technology, there will always remain regions whose light will never arrive. The expansion of space permanently separates vast portions of the universe from one another, creating cosmic islands of visibility that drift apart over time. From Earth, humanity occupies one such island. The Milky Way exists inside a small, gravitationally bound group of galaxies that includes Andromeda and several dozen smaller companions. These galaxies will continue interacting with one another long after most other systems have disappeared beyond the observable horizon. In fact, the Milky Way and Andromeda are expected to merge billions of years from now, forming a larger elliptical galaxy that will slowly evolve while the rest of the universe drifts ever farther away. Yet even this immense cosmic story takes place on scales that remain almost impossible to visualize. The human brain evolved to understand distances measured in meters or kilometers, perhaps thousands of kilometers across continents and oceans. Cosmic distances exceed those familiar scales by factors so large that they lose intuitive meaning. A single light year represents nearly 10 trillion kilometers. The observable universe stretches across tens of billions of those light years. Between galaxies lie vast regions of intergalactic space so empty that a spacecraft traveling for millions of years might encounter almost nothing at all. Despite this immense emptiness, the universe remains filled with structure and activity on every scale that can be observed. Stars continue forming inside cold molecular clouds scattered throughout galaxies. Supernova explosions scatter heavy elements across space, enriching the material from which new stars and planetary systems will form. Black holes merge deep within distant galaxies, sending ripples through space-time that travel across the cosmos as gravitational waves. These waves stretch and compress space itself as they pass, carrying information about events that occurred billions of years ago. The ability to detect such phenomena represents one of the most remarkable achievements of modern science. Instruments sensitive enough to measure distortions in space-time smaller than the width of an atomic nucleus now allow astronomers to observe collisions between black holes across enormous distances. Observatories positioned on Earth and in space work together to build an increasingly detailed portrait of the universe, combining information from light, gravitational waves, and high-energy particles arriving from the depths of space. Each new method of observation reveals additional layers of cosmic complexity. Some galaxies host powerful jets of energy, driven by matter falling into supermassive black holes. Others contain vast clouds of gas illuminated by newborn stars. In still other regions, entire clusters of galaxies collide, releasing enormous bursts of radiation and reshaping the structure of the cosmic web. These events occur across distances so large that they unfold simultaneously in countless locations throughout the observable universe. Seen from this perspective, the cosmos appears less like a static collection of objects and more like a dynamic system constantly evolving under the influence of gravity, energy, and time. Galaxies grow, interact, and sometimes merge. Stars ignite, shine, and eventually collapse. Matter flows through the filaments of the cosmic web, while dark energy slowly stretches the universe ever larger. Over billions of years, these processes transform the structure of the cosmos, shaping the patterns that telescopes reveal today. The deeper astronomers look, the further back along this timeline they travel. Observations of distant galaxies allow scientists to study how structure formed during the earliest epochs of cosmic history. Measurements of the cosmic microwave background reveal conditions that existed shortly after the universe became transparent to light. Particle physics experiments recreate tiny glimpses of the extreme energies present during the earliest fractions of a second after the Big Bang. Together, these lines of evidence combine to form a coherent narrative, describing the evolution of the universe from its earliest moments to the present day. The cosmos began in a state of extraordinary density and temperature, expanded rapidly, cooled, and gradually formed the structures now observed across the night sky. Invisible components such as dark matter shape the gravitational framework of galaxies, while dark energy continues influencing the expansion of space itself. Yet the deeper that narrative becomes, the more it highlights a remarkable truth. The universe that can be observed represents only a portion of what exists. Beyond the cosmic horizon lie regions whose light will never arrive, separated by distances that expansion continually increases. In those unseen regions, galaxies may form and evolve just as they do within the observable universe, following the same physical laws while remaining forever beyond observation. This realization transforms the meaning of exploration. Humanity's study of the universe does not reveal a complete map of existence, but rather a growing understanding of one vast region within an even larger whole. The observable universe becomes a laboratory for studying the laws of nature, allowing scientists to infer how matter, energy, and space behave on the largest possible scales. In that sense, every observation carries both knowledge and humility. Each galaxy image captured by a telescope represents a small fragment of cosmic history reaching Earth after a journey lasting billions of years. Those photons provide direct evidence of events that occurred long before human civilization began. Yet they also remind us that countless other events are unfolding across the cosmos whose light will never reach this small planet. The universe, therefore, remains both accessible and mysterious. It reveals extraordinary detail to those who observe it carefully, while simultaneously concealing the majority of its expanse beyond an unreachable horizon. Modern cosmology stands at this intersection between discovery and mystery, continually expanding humanity's understanding of the cosmos while acknowledging the limits imposed by the very structure of space and time. Perhaps that balance between knowledge and mystery is what makes the universe so compelling to explore. Every improvement in technology allows scientists to push the boundaries of observation slightly farther, uncovering galaxies that formed closer to the beginning of cosmic history and structures that span ever larger distances. At the same time, those discoveries reinforce the realization that the observable universe represents only one chapter in a much larger story. For now, humanity lives during a rare and fortunate moment in cosmic time, a period when the universe remains rich with visible galaxies and energetic processes that can be studied across enormous distances. The night sky still carries signals from billions of years of cosmic evolution, allowing observers on a small planet to reconstruct the history of the cosmos through careful measurement and observation. Long after those signals fade and distant galaxies slip beyond the horizon, the universe will continue evolving in ways that future observers may never fully understand. But for the present generation of explorers, the cosmos remains open to investigation, filled with light from ancient stars and galaxies that have traveled across space for billions of years before arriving at our telescopes. In those faint photons lies the story of a universe far larger than imagination once allowed. a universe whose true scale extends beyond every horizon that can ever be seen.